Graph representation. A graph is a data structure comprising a set of vertices, also known as nodes, and edges. There are two primary methods to store graphs in a computer memory. The first one, sequential representation, also called as adjacency matrix representation. Second one, linked list representation, also called as adjacency list representation. Let's first see the sequential representation. In sequential representation, an adjacency matrix is used to represent the relationship between the vertices and edges in the graph. This approach can be applied to various types of graphs, including undirected, directed, weighted directed, and weighted undirected graphs. If adjacency of I and j is equal to w, it indicates an edge exists from vertex I to vertex j with a weight of w. In an undirected graph, the adjacency matrix entry Aij will be 1 if an edge exists between the vertices Vi and Vj, otherwise it will be 0. For an undirected graph with n vertices, the adjacency matrix is an n cross n. A is equal to Aij, where Aij is equal to 1 if there is a path between Vi and Vj. Aij is equal to 0 otherwise. In this representation, a value of 0 in the matrix indicates no connection between nodes. A value of 1 indicates the presence of path. If the graph does not have self-loops, the diagonal entries of adjacency matrix will always be 0. In the figure, we can see that image illustrates the connection between the vertices A, B, C, D and E. Represented using an adjacency matrix, the adjacency matrix differs for directed and undirected graphs. In a directed graph, an entry Aij will be 1 only if there is an edge directed from the vertex Vi to vertex Vj. Adjacency matrix for a directed graph. In a directed graph, edges indicate a specific direction between the vertices. For example, if a path exists from vertex A to vertex B, it means A is the starting node and B is the ending node. Let's refer to the directed graph here and construct its adjacency matrix accordingly. So this is the adjacency matrix of this graph. Adjacency matrix for a weighted directed graph. The adjacency matrix for a weighted directed graph is similar to that of directed graph, but instead of using 1 to indicate the presence of a path, the weights of the edges are used as the entries. These weights represents the cost or values associated with each edge. To understand this better, consider the example here. The graph and its adjacency matrix representations show how weights of the edges are reflected as the entries in the matrix. In the image, you can see the adjacency matrix representation of the weighted directed graph differs from the other representations. Here, the non-zero values are replaced with the actual weights of the edges. The adjacency matrix is straightforward to implement and understand. It is particularly useful for dense graphs with a large number of edges. Although using an adjacency matrix has its advantages, it is space inefficient. Even for a sparse graphs, and adjacency matrix requires the same amount of space, regardless of the number of edges. Linked list representation. In the linked list representation, an adjacency list is used to store the graph in computer's memory. This method is storage efficient since only the edges values are stored. Here is the example of adjacency list, the representation of undirected graph. In the figure shown here, you can see that each node in the graph has an associated adjacency list. For example, vertex A has the paths to vertices B and D, which are linked to A in the adjacency list. An adjacency list is created for each node in the graph. It stores the node's value along with the pointer to the next adjacent node. Once all adjacent nodes are traversed, the pointer field of the last node in the list is set to null. In an undirected graph, the total length of all adjacency list is equal to twice the number of the edges. Now let's consider a directed graph and examine its adjacency list representation. In this representation, you can see that each node's adjacency list contains only the nodes that can be reached through the outgoing edges from that node. For a directed graph, the total length of all adjacency list is equal to the number of the edges in the graph, as each edge is represented once in the list. Now let's consider weighted directed graph and explore its adjacency list representation. In this case, each entry in the adjacency list will include both the adjacent node and the weight of the edge connecting the nodes. In a weighted graph, each node in the adjacency list includes an additional field to store the weight of the edge connecting it to the adjacent node. An advantage of using an adjacency list is that it is easy to add a new vertex. Additionally, because it uses a linked list, it is more space efficient compared to the other representation.